Anybody worked with logarithms before? Maybe? Okay. So today we're going to look at, when you deal with exponents, it's really useful to be able to deal with logs because there's a pretty direct connection between them, and that's that they're the inverse between each other. So first of all, let's just talk about the notation. If you see something like this expression here, this is read as log base 9 of 81 is 2. Now some of you that are good with patterns might be able to pick out what it means, but what it means is that 81 is the second exponent of 9. So what logs do is whenever you're using a logarithm, it's telling you what the exponent was, right? Normally when you have an exponent, you give it that exponent there, and it tells you what the number is. Now you give me a number, I tell you what the exponent used to be. A couple of things here as well, just notation-wise. Log in base 10, this is called the common log. And we usually just write it as log. We drop the base. So whenever you don't see the base written, you can safely assume it's base 10. And we are going to talk lots about this one in calculus, but the other one, you'll notice it's on your calculator as well. This one is the natural log. And this is the log in base e. E is Euler's constant. So to get started, we're going to just practice going between logs and exponents just so that you get the hang of it. In the first instance then, if we look at 9 equals 3 squared, and I want to look at it as a logarithm, from the logarithm point of view, it has the same base. So that's what I always start with. The first one is easy because they both have the same base. But remember, a logarithm wants to know what number did you use. The number I used was 9, and the exponent I got was 2. So this is saying what exponent of 3 is 9, and the answer is 2. So while you're getting the hang of it, this is the exponent that goes here. This is the base. And this is my number that's base to exponent. Oops, too many. So this should become second nature to you at some point. You shouldn't need to refer to that little diagram. So let's talk about the second one. Okay, this is a log in base 2. Okay, so there you go. First part's nice and easy. Log is in base 2. Okay. Now, at this point, you have a 50-50 shot with those numbers, right? So which one's the exponent? Exponent go here or here? Yeah, it goes on the right side because the logarithm will tell you what the exponent equals. So exponent is -2, which means a quarter is the only thing left. It goes here. And again, if you're getting used to what a logarithm is, this says that 1/4 is the -2 exponent of 2. All right, you try the next one. So you should have something like log base 2 of 8 equals x. Remember, the exponent is what it's equal to. The base is the same. And the number it came from, in this case 8, is going to be log base 2 of 8 equals x. Okay, we should be able to do the other way as well, which means, can you rewrite this as an exponent? This is more natural to most people because this is what the world you're used to. Like, how do you make an expression out of 3, 9, and 2 if you had to use exponents? What would it look like? 3 squared equals 9. it's the same process. The base is 3. Right, here's my base. And my exponent is 2. Okay. So even if we change it and we throw a fraction at you, how could you write this one as an exponential form? Yeah, 3 to the negative 3 is 1 over 27. Okay, now this time we're throwing a letter at you, so what would it be if I asked for log base 4 of x equals to 3? How could you rewrite that? 4 cubed equals x. That's right. So that's a real simple one. If you had to solve, like, what is the value of x? Well, if 4 cubed is the value of x, so in this case you could even tell me it's 64. Okay? So let's try and do some of these now without a calculator. We'll talk about how to use your calculator soon, but for now, can you evaluate log base 5 of 125? At this point, if the first thing that comes to your mind is anything other than exponent, you're doing it wrong. Remember, a logarithm will always tell you the exponent that you're dealing with. So this is saying what exponent is 125 if 5 was the base? Yeah, it's cubed. Good. So think, what's the exponent I'm looking for? That's what we're dealing with right now in logs. Okay. This one's a little bit bigger. 3 to the what is 729? Okay, so that one is 6 because 3 to the 6 is 729. Now, if you're in a situation where you're not able to use a calculator, the numbers will be small enough that it'll be, practical for you to do. So this one borderlines on a little difficult without your calculator there. But anyways, I would say generally you'll be dealing with exponents less than or equal to 5, something more manageable. How about this one? Yeah, negative 4 is right. Wow, you're on you must have had coffee this morning. Okay, so now let's think about what we could do here. If we had to figure out what's the missing value in the expression, right? What makes the relationship here true? How could you figure this out? What would x be in the first one? Yeah, it's saying 10 to the power of 2 is going to be this value here. So okay, what about the next one? Two is correct. It's x to the 8 is 256. So this would be one that a calculator would be appropriate for, I suppose. You'd raise both sides to the 1 over 8, take the 8th root, and then that way I get x equals to 2. So log equations is something we're going to spend more time on later, but right now let's just try some simple ones. If log base 5 of x plus 3 equals 5, we can solve that by going 5 to the 5 is x plus 3, and that's certainly a large enough number that merits a calculator. So that's 3,125 is x plus 3. So x is equal to 3122. Okay, so the other one's a little more manageable. See if you can do it without your calculator. If you have to, go for it, but see if you can try the next one without a calculator. So in this one, x is 114. Okay, so just a couple of refreshers because we are going to be talking about the graphs as well. I don't know if you're in this habit, but this is one that I always tell people. When you hear x or y intercept, you have to think something else. When you hear x intercept, what you should think in your head is y equals 0. Because if you're touching the x-axis, then there's extra information there. You might forget. It means y equals 0. And in this case, if you're touching the y-axis, x must be equal to 0. So if I wanted to look at something like this and find the intercepts of it, let's start with the y-intercepts. So for the y-intercept, x must be equal to 0. I can use that to figure out what the y value must be. So log base 2 of 4, what's that going to be? Two, yeah. So y is 6 minus 24. So it's going to be negative 18. So the y-intercept is negative 18 on this graph. Okay. We also want to find the x-intercept. So the x-intercept is going to be when y equals to 0. Okay. So let's try and solve this equation then to figure out the x-intercept. 24 would be 3 log base 2 of x plus 4. If I divide both sides by 3, I'll get 8 is log base 2 of x plus 4. And now I can use that equation. 2 to the 8 equals x plus 4. Rewriting it as an exponent, so 256 is x plus 4. So x in this case is 252. Okay, so that was finding the x-intercepts using y equal to 0. So that's so far just manipulating these things between logs and exponentials. That's really all we've had to do here is know a little bit about what a log is and how to switch between log and exponential. But we're also going to take a look at some identities. So the first identity goes like this. Log base 10 of 10, help me out here. What would that be? 1, yeah. Log base 5 of 5. And log base 23,846 of 23,008. Do you want a calculator for that? It's 1, right? It's basically you're using the same number. So if you have log base a of a, it's just going to be 1. You could simplify that down. And then another one which is kind of tricky that people seem to forget about, log base 10 of 1, what would that be? 0. Yeah, 0. So log base 5 of 1? Yeah, all these are going to turn out to be 0 because any number to the 0 exponent is going to be a 1. So that's what we can say about this little property here. Okay, so those are just two that, I don't know, as simple as they are when you do exponents, for some reason can be tricky for people doing logs. So we're going to work these ones out. But we're going to do it one piece at a time and see what happens. So first of all, I'm just going to look at the top here. What's log base 10 of 100? Yeah, that's 2. So what's 10 squared? Good, 100. Okay, let's try it again over here. Log base 5 of 125 is? And then 5 cubed is? 125. Okay, do you want to take a shot at it? What will log base 3 to the log base 3 of 243 be? 243. So someone's found a pattern. Do you see what's happening here? Yeah, what we started with and what we end up with, oops, too much, are the same because I've got the 100 that shows up here is the answer here. 125 is the answer here. 243 is the answer here. Why is that? Well, the connection between logs and exponents, they're inverse to each other. So when I go exponent and I raise it to a logarithm, the two cancel out because they're inverses, right? So if I had the same base raised to its logarithm, it's just going to turn out to be x. Whatever the number was that you started with. So this is really just the property that the two are inverse to each other. You raise one log base 10 of, 10 to the log base 10, you'll just get 100 back for this one because they cancel each other out. Okay, think about this one now. 10 squared is, and log base 10 of 100 is. Okay, how about this one over here? 5 cubed is 125. So log base 5 of 125 is 3. Okay, how about the last one? Can you see the pattern? It's going to be 5. So why is it that it keeps turning out like that? They're inverses of each other, so it's just the same thing the other way around. The logarithm of the exponent or the exponent of the logarithm, right? They're inverses, and you're using the function and its inverse. So in this case, that exponent is the only thing that survives. Okay, so now you should be good at something like this. Log base 3 of 27 is going to be 3. Good. Okay, but then it gets tricky for some reason if I throw a square root at you. Yeah. What about this one? Ooh, yuck. Well, let me show you a little strategy here that kind of comes in handy with what we just talked about in those identities. Remember how we rewrote the numbers with a different base when we did exponential equations? What if instead of looking at it this way, I could call this log base 3 of 3 cubed, right? 27 is 3 cubed, so that means the only thing that survives is that exponent 3. The same thing happened over here. This is log base 5 of 5 to the 1/2. So the only thing that survived was the 1/2, okay? So if you can't figure out what this is just by looking at it, I mean, everybody knows what the log base 2 of cube root 64 is. No, they don't. I'm just, anyway. So try and rewrite it in base 2, okay? Can you rewrite this as log base 2 of 2 to the what? Okay, so if you are comfortable with exponent laws, then you could start by writing this as log base 2 and just call it 64 to the 1/3. And 64 is 2 to the 6. So that means I've got log base 2 of 2. Multiply those exponents, right, in the log laws. So this is going to be log base 2 of 2 squared. So now it's easy to see what my answer is. So this is the only thing that's going to survive because this is a function to its inverse, which is going to just end up being 2. Okay. All right, so how appropriate. We just had an earthquake drill. I didn't plan for this, by the way, but anyways. An earthquake with magnitude 7.5 is measured off the coast of Vancouver Island in the town of Tofino. An aftershock is felt with magnitude 4. How much stronger is the earthquake than the one in Tofino? Now, has anybody been in an earthquake before, like a real earthquake? Sort of, okay. Now, if somebody says, oh yeah, you know what, I was in a magnitude 4, you guys must remember the earthquake. We had one in Vancouver like, I'm going to guess 10 years ago or so. Wow, thanks for making me feel old, Danielle. Anyways, if someone's like, yeah, you know what, I remember what it felt like in a 4, and you're trying to describe what it was like in a 7.5, they don't seem like they're very far apart, but the Richter scale is a log scale. What happens is the amount of energy that's shaking the Earth gets so big so quickly that you don't want to talk about it like I was in a magnitude 10 trillion earthquake. It just sounds silly. So what they do is they log the number down. So this is what they actually mean. This is 10 to the 7.5 versus 10 to the 4. So they use the common log, and they take that number and they log it down. So that way you don't deal with 10 to the 4, you just say magnitude 4. So if we're trying to compare these two earthquakes, this is how we'll do it. We'll just divide them to get the ratio, right? Find out how much stronger it was. And if you know your exponent laws here, this will be 10 to the 7.5 minus 4, which is 10 to the 3.5. And that's 3,162, and we'll stop at 0.3, times stronger. So it is pretty misleading. Like, you might wonder, like, oh, it's kind of weird. We always hear these 6 and 7s. How come we didn't hear many 8s or 9s? Well, it's a good thing, because to go from a 7 to a 9, that's 100 times worse. And you know how much damage happens in a 7? Well, keep going, right? So you don't see these earthquakes very often getting that high, but it's because it's in a log scale. There's lots of other log scales, like those of you who like blowing your eardrums out with your iPod or your iPhone. The decibel, the bells are measured in a log scale as well, and pH, chemistry. So this one is also, it's not that it has a pH of 4.3. The actual measurement, and again, we're not going to learn about chemistry in math class too much, but the actual measurement would be so big, it's not practical to talk about it this way. So just out of practicality, we take the logarithm of it, and we only deal with 4.3. So if we're talking about lemon juice versus soap, and you want to know how much more acidic is lemon juice, then, oops, you've got 10 to the 8.4 for soap, and 10 to the 4.3 for lemon juice. So that's 10 to the 4.1, I think. Yeah, 10 to the 4.1. And that's 12,589.3. A lot won't count, by the way, if that's your answer in the written or a quiz or something. But yeah, usually between these scales it gets big very quick. Okay, so log scales is one big application for logarithms, and of course we're going to see lots of applications in logarithms, because anywhere we're solving an exponential application, you're going to run into a logarithm as well. So the last thing we need to do today then, now that we've sort of introduced you to logs, is be very clear about what we mean about an inverse. So I've told you it's an inverse, but you might be like, well, okay, great. Let's take a look now at actually how it works. So if this was your function, y equals 2 to the x plus 1, everything is as you knew it before for an inverse. You're going to switch the x and y. But in order to solve for y, you need a new tool. You need logarithms in order to solve for an exponent. Anytime you want an exponent, that means you need to use a logarithm, right? That should be in your head now by the end of this block. If you want an exponent, logarithms are going to help you. So in order to log this, I'm going to have to isolate that. So now all I have is the base to an exponent, and it's going to be equal to some number, which I know it looks weird as x minus 1, but that's just a number, like, you know, 1,000,000 minus 1 or something. So if I rewrite it in log form, I'll be able to solve for y. It'll be the log in base 2 of x minus 1 is equal to y. So this here is the inverse to this equation here. All right, so just practice that one for yourself. Try it on this equation here. Find the inverse to 5 to the x plus 1 minus 4. Okay, so if you were on the right track, let's see how you did. I'm going to switch x and y, like I always do for inverse. And now I'm going to try and isolate it, so I have x plus 4 equals 5 to the y plus 1. And now I know this is a log in base 5 of x plus 4 will be equal to the exponent, which is y plus 1. So I might as well write this in standard form. It would be log base 5 x plus 4, and I'm subtracting the 1. Move it to the other side. Okay. So it's identical when you go the other way and you want to get back. Sorry, did people need to copy that any more of that? It's identical when we go the other way. We're going to start by switching x and y. So x is equal to log base 3 of y plus 2 minus 1. But now the only way you can get that y outside of the logarithm is to rewrite it in exponent form. So it'll be x plus 1 is the log in base 3 of y plus 2. So 3 to the x plus 1 is y plus 2. And I might as well write it in the standard form. This would be my inverse. Alright, so just to make sure you've got the hang of both ways, try this one here on your own. See if you can find its inverse. Okay, so in case I'm a little sleepy, can someone just confirm for me that that's what they also had? All right. So, nice work then, everybody. Logs, are they super scary? Not so much? Okay, good, because it's one of those things, it's like you guys know so much math that logs is the first new thing you've learned in a long time, so sometimes people get scared off. But so you're on your own here to work on the homework for today?